Hello everyone and welcome back to the channel. I am recording this video on September 6, 2024. And the reason I make note of that is because of the fact that despite it being literally the first week of September, it is already in the 60 degrees range here in Chicago, which fucking sucks. I will say that if there was ever conclusive proof that Jews do not in fact control the weather, it would be right now, because if I could control it, it would be 80 degrees and sunny. Nonetheless, I live in this absolute barren, frozen wasteland, and here we go. The one possibly good thing about it getting colder is that football is back, and so at least I have that much to look forward to. Anyways, besides football, I also have a lot of systems design papers and distributed systems papers to look forward to, so let's go ahead and cover another one. Okay, so today we are going to be talking about Dremel. So Dremel is a paper out of Google that came out in 2010, and it is an ad hoc querying system, which basically means that, if I'm someone like a data analyst or a data scientist or a business analyst, someone whose job it is to mainly try and derive insights from big data and run all these queries that I personally can analyze, Dremel is going to be what I'm using a lot. And the fact is, when you have a lot of these employees, you're running a lot of these queries, it's important that they run fast. If you can make one of these queries 50% faster, and you can basically make it such that this person is now running 50% less time on all of their queries, all of a sudden you've just made tons of your employees a lot more productive, and that's a big deal. Hence, it's important for Google to focus on a system like this. Another thing to note about this querying system in particular is that it operates in situ. In situ just means in place. It's a term that they use a lot throughout the paper, so I think it's important to specify it. But of course, this is still at a point where network bandwidth speeds are going to be a bottleneck for a company like Google. And as a result of that, it's very nice to minimize the amount of data transfer that they do when making all of their queries. Now, conveniently, the sun has decided to go ahead and shine right in my face. So sorry if the camera gets a little bit weird, but I'm just going to hope it goes down another 30 seconds. So another piece of this is because of the fact that we're operating on data in situ, it means that a lot of our actual Dremel nodes are probably also going to be co-located with something like a big table or a GFS process so that we can quickly access all of that data. Great. So the last piece of this is that we may actually use Dremel to replace certain MapRuce jobs, right? You can use MapRuce to perform things like arbitrary querying. However, Dremel is going to be the better tool for the job for a lot of these ad hoc queries that are going to be run by humans. It may not be a better thing for something like an ETL job where you're taking one data set and converting it to another, but for something like an ad hoc query, it is totally going to be a better choice. That being said, like I mentioned, it is not going to get rid of MapRuce completely. It's going to be a complementary tool. Cool, so let's talk about a nice example use case for when we might want to use Dremel. Let's say I'm a dev or a software engineer. My company calls them devs for some reason because they're not a tech company. And basically, if we're talking about devs, then maybe I'm trying to build an ETL job or some sort of data pipeline. First thing I want to do is take my input source and use Dremel to inspect it. Maybe learn a little bit about the data. Hey, what would I do if I were trying to make some aggregations on this? What do my initial statistics look like? And then eventually I would write up some MapRuce job to actually convert dataset A over into dataset B. And then finally, maybe I want to validate and confirm that the MapRuce job that I built was actually successful. So I'm going to now go ahead and use Dremel queries to validate the correctness of that. Now the sun seemingly is just getting worse and worse in terms of bodying my face here. So that's not ideal, but we're just going to work through it. So again, that is a good example of how you might use these tools in tandem. Cool. So at a high level, let's go ahead and talk about some Dremel performance optimizations before we actually jump into them. Number one is that Dremel is going to allow us to use nested data. So this is very nice in terms of denormalization, right? Because if we were talking about a typical SQL database, if we wanted to basically express some sort of row having a bunch of inner nested data, we would basically have to use multiple tables and join them together. And it turns out that at such a massive scale as Google often operates at, those massive distributed joins are not as feasible. And a lot of the time, you can actually just keep everything in one row and keep it denormalized. And so basically that's what Dremel is going to allow us to do. So we avoid these distributed joins, and ideally the majority of Dremel queries are going to allow us to focus on these major kind of aggregation queries, where we do one pass over the data, we do some selecting and then maybe filter down that data a little bit with where clauses. We might do some projecting or transforming the data with the select blank from whatever. And then finally, we might aggregate it, right? Things like sums, group bys, anything like that. we're basically taking a large amount of data and condensing it into a much smaller bit of it. And so what is going to really help us to do all of that is using column-oriented storage, because Dremel is going to be operating on really massive data sets, and a lot of the times you only need a subset of that. So in the case of column-oriented storage, if we have this table with hundreds of fields where a lot of those fields are sparse, rather than trying to read all of those, we can actually just read the columns that we need. And in addition, of course, when you're using column-oriented storage, another big benefit that you get is going to be compression. So that's useful as well. But again, if we only read the data that we need, because many of these tables do have tons of fields and the majority of those fields are not going to be useful at a given time, we can save orders of magnitudes of performance. Finally, Dremel introduces a concept called the serving tree. So basically, this is multiple levels of data aggregation. So I'm going to have many, many nodes because I'm doing a distributed query. And this is going to allow us to basically aggregate them quickly along these nodes in kind of a tree formation. So we'll talk about that in a bit. And then finally, we can also deal with approximate or incomplete results. Now, when I say approximate results, I don't mean pretty off. I mean like very, very, very close to being right. However, one of the concepts that we've talked about a lot in the past is stragglers. So this came up in the MapRuce paper. You're welcome to watch the video on that one. But the gist is, when you're running multiple distributed jobs, some of them are just going to be a lot slower than others, possibly due to bad hardware or something like that. And as a result, they're going to take disproportionately long to complete. And so potentially throwing out those results might help us out a lot. Okay, so the first thing that we're going to talk about is protocol buffers. So we've spoken about protocol buffers plenty on this channel before, and the gist is it's a data encoding library, right? It allows us to basically specify a schema for our data, encode it in a more efficient way than if we didn't have a schema and we're just using something like JSON or XML or something like that. And in addition, in this case, Dremel actually makes it so that you can go ahead and use protocol buffers to define a schema and then actually store that data in a column-oriented format. Now, this itself would be somewhat trivial, but the interesting thing with protocol buffers is that they allow both nested fields and they allow repeated fields. And so it's not actually trivial to actually store these guys in a column-oriented format, because then you actually have to figure out, hey, if I have uneven amounts of data for all of these fields, which field basically belongs to which row on the table. So to kind of show that off, imagine we have some person object in protocol buffers, and person has a field name, and it also has a repeated field or a list of fields called interests. And so basically, sorry for turning off the Wi-Fi there, I don't want everyone to see my texts. Basically, the gist is, if we go ahead and have a couple of names here, right, so we've got maybe a name with value 1 and a name with value 2, we might have 3 interests for person 1 and 2 interests for person 2, but the gist is there that how are we going to basically back out which one belongs to which? So I'm going to cover that a little bit. I'm basically going to give a major disclaimer now, right? The paper spends a significant amount of time, I would say the majority of the complexity of this paper is kind of explaining how they actually go ahead and encode the data in protocol buffers in a way that is compatible with column-oriented storage. Now, the truth is, if you're just interested in distributed systems, I don't think this is going to be that relevant for you, frankly, because it's kind of more of an algorithmic thing. I'm going to try and cover it to the best of my abilities, but truthfully, they don't do a great job of explaining it in the paper, and so I, in turn, am also not going to do the most fantastic job of explaining it. Nonetheless, I'm going to give it an attempt, and if you don't get it, again, I always link the paper so you can try and reference it yourself, but frankly, I don't know if it's going to help you that much more. Cool. So let's take a look at protocol buffers, right? We have this concept of a schema over here on our left. And so in a schema, we have something like a message, or basically, some sort of outer record type. We have fields that can be required. We have basically optional fields. We have repeated fields. And then we also have, inner fields in records. And so things like that are also able to make it so that, this gets a little bit more complex to encode and decode. And so let's look at an example of something that defines this schema, right? Because we're going to use this example in the next few slides. As you can see, I finally figured out how to attach images in my iPad, so it's over for everyone at the moment. Basically, as you can see, I've got my document ID filled out. This link section is basically optional, but it is going to be filled out here. We can repeat this forward key multiple different times because of the fact that it is repeated. Repeated fields don't have to be defined at all, so note how the backward field is not defined in this record. And then of course you've got a repeated name field, so we see 3 of those over here. Within names you can have multiple languages. Within a language you can have, you have to have a country actually, or rather you have to have a code, but it is optional to have a country. So again, hopefully this gives you a sense of the data that we're working with, because we're going to work through this example in the next couple of slides. Okay, so the first question is, well, when we write down our data in our column-oriented format, we have to basically split it up by column, right? Or basically split it up by individual field. And so the question is, we need some sort of metadata with every single field in order to eventually back out which record that field belongs to. And so this is how Protocol Buffers basically chooses to do it. It defines a couple of numbers, one called the repetition number and one called the definition number. So I'm going to explain right now how you would compute the repetition number. Okay, so this is going to first start with me giving out the high-level algorithm of how you would do it, and then from there we'll go through an example, because again, it's really not explained too well. So basically, if I have a field, right, let's say I want to find the repetition number for this guy over here. I just linked it, but it's forward 60, right? So the path of forward 60 is the following. It's .id, .links, .forward. And the value is 60. So the idea here is, okay, we want to basically find all of the repeatable fields in that field's path. So in this case, the repeatable fields in this field's path is just going to be the forward field, right? We include the field itself in the full path. Cool. So now what we're going to say is, for this field, we're going to find the lowest field in the parent list. So right now, the parent list of repeatable fields is going to be 1 indexed. So I'm going to call it forwards, or forward, with an array of 1. Cool. We're going to say find the lowest field in the parent list that is already repeated. So in the example of this one, where the value is 60, you might notice that, oh, wait a second, we've already defined forward, okay? We've defined it right over here when the value is 20. And so as a result, basically the lowest value in this, or rather the forward field is already defined, so the repetition level is going to be 1. In the case of forward over there, right, .id, .links, .forward 20, you may note that it is the case that the list of repeatable fields is the same, right? It's still going to be forward indexed at 1. However, the major thing to note here is that forward has not already repeated yet when we're reading this path. And so because forward has not repeated, we actually hit our edge case, right? If none, return 0. So when we see 0 on a repeatable field like this, it basically insinuates to us that we've started a new document. And that is going to be the case here, or rather that this is going to be the first field of its kind within a document. Now let's back it out for something like this guy, right? Hopefully this isn't too hard to see, but the gist is I'm circling the code English, right? So this is going to be name.language .code. And as we can see, it's being set to English. So in this case, the repeatable fields, as we can see from our protocol buffer schema, are both going to be name and language. So it's name, language. And because it's 1 indexed, we have a 1 to name, a 2 to language. In particular, for this code English, we want to say, okay, what is the lowest level field that's already been repeated in this record that we've already seen, basically. And so you can see, oh, wait a second, well, between name and language, I have already seen name, and that's okay, but more importantly, here, I've already seen language. And so as a result of that, that means, language is the lowest level repeated field, and so we choose that, and hence the repetition level of this guy is 2. And so I've basically outlined all of the repetition levels here for you guys to check. We can try doing one more if you'd like, but I'm trying to think of the best way to do it. Let's go ahead and choose this, this country guy. So country is Great Britain. So the schema of country is name.language.country. Note that in this particular record, we basically do see that language has not yet repeated just in this record over here, right? But name has repeated because in the outer schema of, like the range of repetitions, name has been repeated. So in this case, we choose name is equal to 1, and that's why the repetition level for this field is 1. So again, I know that's kind of hard to explain, and frankly, I don't think they explain it any better in the paper. I read through this for literally hours to try and get that piece down. But yes, this is the repetition field, and you'll see how it comes in handy in a little bit. Cool. The last piece of this, which I'm going to touch upon very briefly, is that if we have a required field, and basically it has an optional parent, or a repeated parent, but that parent is undefined, we're going to have to include that in our column for that particular field with a null value and its repetition value. Okay, the next piece of this is going to be the definition number. So similar, again, we're going to look at the full path of a given field, and we're basically going to check how many of the repeated and or optional fields in the full path that we have that are present. Cool. So in the case of this guy, right, forward 20, again, I'm sorry if this is hard to see, but that's why I'm drawing an arrow out here. We've got links dot forward. So note that this is both repeated and optional. Links is going to be optional, and forward is repeated. And so both of these guys are defined for the particular value where the field is 20. Hence, it has a definition level of 2, because we're just saying here's 1, here's 2. Let's try and find a different example. How about this guy over here? Name.language.code. So name is going to be repeated. Language is going to be repeated. Code is going to be required. So required, repeated, repeated. Hence, our definition level, again, is 2, because only these guys are going to count towards our definition level. Okay, another thing to note is that even if a field itself is going to be null, if it has a non-zero definition number, we must record it in basically the column definition for that particular field value, right? So I'm trying to think of a good example of this, but the gist is, you may have a null field, because like we covered over here, you can have null fields, but certain fields are optional, but they may have optional parents that are actually defined, and so then you do need to actually write the fact that that exists somewhere with its definition number. Cool. So ultimately, what is this going to build us out? Well, let's say we've got some field 1, field 2, and field 3. All we're going to be doing is writing these sequentially in our column-oriented storage with their value, their repetition number, and their definition number. Now, a few small facts here to add, not overly important, but just to note. Within a column, obviously, we're doing compression as much as possible because we want to limit the amount of space that we're using. Number 2 is that our definition number is going to be used as an indication that a field is going to be null, right? So if the definition number of a field is less than what it could be at its full length, because it's an optional field and it's less than that, then the field must be null. Number 3 is that we can also perform bit packing on some of these numbers. What that means is that, let's say I only have possible definition numbers 0 to 3. Well, that's really just 2 bits, right? There's 0, 0, 0, 1, 1, 0. So I'm not going to store like a full integer or something and use a bunch of bits or use a bunch of bytes. I'm just going to store a couple of bits. Cool. Now let's talk about decoding, which I think is probably a little bit more interesting here, but again, I still think may leave a fair amount of questions open, which is why I was a little bit hesitant to cover this stuff in the first place, but let's talk about it. So basically, when we're decoding the fields, we construct something called a finite state machine. So the finite state machine is actually pretty simple, conceptually speaking. Basically, what you do is you start at the top level field. So in our schema from earlier that we have shown over here on the left, the top level field is going to be the document ID, right? So let's say the document ID is written just like this in column-oriented storage, right? We have one document where the document ID is 10, and then in our second document, the document ID is 20. Basically, what we're going to do is we read the document ID field, And then we look at the next one. So I've read 10, I see it's 0. And then I look at the next one, 20, I see its repetition level, and I say, ooh, shoot, you know what, that's a 0. That means that this 20 is actually part of a new row in our database table. And so before I go ahead and read that document ID in particular, what I want to do is now start iterating to the other fields in my current record. And so we build out this finite state machine that actually uses the repetition levels to very conclusively and deterministically tell us exactly which field we should be reading based on the repetition level of the next field that we're about to read. So for example, if you think about it, I'm going to switch my color to black here because now all of a sudden we kind of want to zoom into this finite state machine. If I'm starting at the document ID field and I'm reading it out a little bit, and I see the next document ID field has a repetition number of 0, it means, oh, you know what, this is clearly the next document ID of the next record. So I want to go ahead and switch and start reading my links. So maybe I'm at links.backward. And we covered how this the forward and backward repetition links work a little bit before. If it's the first one, obviously it's going to have a repetition number of 0. However, sometimes what you're going to see is links.backwards with repetitions of 1. And what that means is it's actually going to be not the first, but an additional links.backward within the record. The same thing applies if we see a 0. If I'm reading links.backward and I see a second links.backward with a repetition number of 0, it means, oh, this is the first links.backward in the record. And so now I have to go ahead and iterate and start reading the links.forward before I open up this new record again. So that's really kind of how this works at a high level. Again, I don't want to explain it too much because we genuinely could be sitting here all day thinking about this algorithm. I would much rather prefer to not do that. So I think that's one interesting piece of this, but another interesting piece of this is, the reason column-oriented storage works nicely is because if we request fewer fields, right, let's say rather than reading every single field in the document, I just want to read document ID and I just want to read name.language.country. Our algorithm is actually allowing us to construct a finite state machine that uses the repetition levels of those fields in the same way as they do before, but then makes a much simpler finite state machine. So we're only jumping back and forth between reading the document ID and the country, right? So let's say, country over here. So, we've got 10 and 20, and maybe we've got a repetition level of 0 and 0. And then over here we've got named a country, so we've got country of the US with a repetition level of 0, and the country of the US with a repetition level, or sorry, not US, let's do, what's another country? The UK with a repetition level of 1. We're just following the state machine, right? So UK of 1, and then maybe eventually we see the US again with a repetition level of 0, or rather than doing the US, why don't I do China, just to make it clear. So we're starting over here. We say, okay, we've got doc ID 10. We see that we've got a finite state machine, or repetition number of 0, not doing anything. Let's go ahead and read doc ID 20. Uh-oh, repetition level of 0. We've got to go ahead and now jump over to our country field. Okay, 0, that's fine. I stay over here because I'm now going to read the repetition level of the next field. The UK is telling me, ooh, shoot, this is number 1, so now I can actually stay here and read the field of the next one. Oh, shoot, we're back to 0 again. Now I have to flip back over here and start reading 20. I see 0, or maybe, I have document 30. I see 0, and then I flip back over to read China, because now China is corresponding to document ID number 20. So you can see it does get a little complex, but you're basically always following that repetition number of the next element in the column, and that tells you where to jump to. Cool. So again, if you don't really understand that much, rather than barrage me with a ton of questions in the comments, I mean, you can. I'm not going to complain that much, but admittedly, this is a very hard subject to explain, and I think they could do a better job of it in the paper. I would recommend reading the paper, first off, before asking me a ton of questions about this, because I know it's coming. Or B, you can accept that it's not that important and that the query execution part is probably a little bit more important. So let's go ahead and talk about that more, because I find it more interesting anyway. Dremel is highly, highly optimized for one-pass aggregations. What does this mean? It means basically that we're doing like a select star from blank, group by blank, and do some sort of aggregation on it. Because those are the type of queries that you run if you're a data scientist. Like, I don't care about queries that give me 1,000,000 rows back because I'm a human being. I can't read 1,000,000 rows. Maybe you care about getting 1,000,000 rows back for a MapReduce job, but as an analyst, I need to condense things into pieces of data that I can actually understand. So this is what we're really optimizing for. And so it's important basically that the final data size, or basically the cardinality of our data at the end of it, is going to be small. That is going to be what works best with these kind of query trees. So basically another nice thing is that because we've nested our data, we can do a lot of aggregations within a record, but we also are going to be avoiding joins as much as possible. Joins makes this whole thing a lot more complicated, and then of course you have to do a lot of different logic to actually work that out better. We've spoken about distributed joins plenty on this channel. I'm not going to cover them too much at the moment. So what Dremel actually does is it goes ahead and creates something called the multi-level serving tree. So right over here we've got our root, and this might just be one query planning node where basically it's going to say, okay, I see that we want to read from a certain table. Let me go ahead and figure out which partitions or tablets or files that I have to read from either GFS or Bigtable. So I'm going to figure out that table metadata, and then I'm going to route all of these queries to the next level, right? So I'm going to assign this intermediate layer to each have themselves a subset of the query. Right, so we basically are now going to go to the intermediate layer, and then the intermediate layer is going to tell this leaf node layer which particular tablets that they're individually going to read. They're going to read those tablets, they're going to do some sort of aggregation locally, and then they're going to push that back up over here, aggregate in the intermediate node, and then they're going to push that back up again, and finally aggregate in the root node. So obviously this is going to allow us to take advantage of a lot of parallelization, right? It's huge for us in the sense that we can merge all of these results together, and the reason this works, and ideally we can avoid getting disk involved too much, is because of the fact that the end result of this query is going to be fairly small. If it's going to be too big, then you're going to have to do things like sorts and making sure that every single one of the same keys is on the same node, and so that's like what MapReduce would do normally. So to speak to that, let's compare Dremel and MapReduce a little bit more conclusively. So what does MapReduce do in its paradigm? Let's say we have the following query, right? Let's select X, take some other field called Y, we want to sum it up, and then ultimately we want to group by X, which is really what MapReduce is doing. We're mapping and then we're aggregating by that key X. So let's imagine the cardinality of X is fairly small. Unfortunately, MapReduce doesn't really care, right? What it's going to do is it's going to take in a row of X comma Y values, and the first thing that it's going to do, or not necessarily a row of X comma Y values, but it's going to take in some input and it's going to transform it to X comma Y values, right? So that's what the mapper is going to be. And then next, as we always do on the mapper, we're going to sort those pairs. Now right off the bat, you might be thinking to yourself, I'm not actually sure this is necessary here. And I think generally speaking, you'd be right. Sorting does have a lot of advantages when we're working with big data sets and they need to fit on disk, because then you can basically do a bunch of merges of really big data sets. But if these data sets are small enough, or eventually they condense to be small enough, you might be able to do the actual aggregation on the X key in memory using something like a hash map. So I think that's worth noting as well. After we do this whole mapper phase, right, maybe we've got our mappers here, we're going to shuffle all the data to our reducers. Now, fair enough, you do have to ultimately send the data somewhere, and that's going to be the case in Dremel as well. That being said, on the reducer now we're going to sum all of these values for Y, and then finally write them to GFS. So at least, they don't really say it explicitly in the paper, but at least according to my own thinking, what I think makes this slow is a couple of things. For one, we don't need to do that sorting step. The aggregation in MapReduce, I think generally speaking, is going to be done where you're like taking the next element up on disk when you're merging all of these sorted lists, and then merging them together and putting them back on disk. And then finally, we're not doing any aggregation on the mappers, right? Our mapper is extracting a bunch of XY pairs, but it's possible that you might already have, if the cardinality of X is low, that you can actually do some reducing on the mappers themselves and then pass that off to the reducer, because that's going to limit the amount of data that you have to send to the reducer over the network and that you have to sort and all that good stuff. And then of course, if you're using MapReduce, you do eventually have to write to GFS, which is expensive. Dremel is just returning you a bunch of data. Cool. In contrast, what does Dremel do? Here, again, we're doing a select X, and we're summing up some other field Y from some random table, and then we're going to basically be grouping by this field X. So let's imagine X has a low cardinality, same idea. Maybe there's only 10 unique X values or something like that. Or maybe there's 100, but even still, it's not going to be massive. Even there could be 1,000. But the point is, as long as there's not 10 million, that's a very different story, right? So we're taking this T. We have our root node over here. T is breaking this up into a bunch of stuff. Maybe it's saying, okay, over here, you're responsible for tablets 1 through 20. And over here on this intermediate node, you're responsible for tablets 21 through 40. The intermediate node is then going to go ahead and basically tell the leaf nodes which tablets they're responsible for. The leaf nodes are going to read from GFS, or ideally even be co-located with them, hopefully in the same data center at least. And then once they get those back, they're actually running this query themselves locally on the leaf node, right? So they're doing this aggregation locally because ultimately this is going to be a cumulative operation. You can basically keep running it on all of the intermediate and leaf nodes and then get the proper answer on our root node. So we're doing this whole query over here, we're doing the query over here, doing the query over here, we're doing the query over here. We then proceed to union these together or add them up, and then again on that result we do the query again because we're still working. Same exact thing over here. We take them over here, add them up, run the query. Same thing, finally we union these two tables together and then we run the query. And so again, this is going to significantly limit the amount of data that we're actually sending over the network, and as long as there's not too many of these X values, we're getting a pretty good result there. Cool, so let's actually talk about a couple of concrete benchmarks that we get out of this paper. So number one is the following. Column-oriented storage is really damn useful. On a table with 300 fields, even if a lot of them are not actually filled in, if we only need the value of 1 or 2 columns, we're looking at potentially an order of magnitude of a performance difference, and that's not just using Dremel, that's just using MapRuce on basically column-oriented storage versus non-column-oriented storage, which is pretty huge. Number two is that on top of already using MapRuce with column-oriented storage, we can get an additional order of magnitude improvement by using Dremel. So again, this does ultimately get done on one of these aggregation queries, right? Again, Dremel is not really made for basically taking one huge data set and converting it to another huge data set. It's meant to condense it down. So that kind of illustrates the impact of the serving tree on this particular type of query. Another thing is that Dremel scales really, really nicely. As you continue to add nodes to your serving tree, Dremel creators saw that they were getting around a linear improvement in performance, which is really, really nice to have. It means that your system is actually scalable. And then finally, of course, same issue as MapRuce, stragglers are going to seriously slow things down. And so this is where data approximation comes in. They found that even if they just set return results after 98% completion as opposed to 100% completion, they would get a significant increase in performance. And so you do honestly take that trade-off in whenever you want complete results. So this is, of course, a tunable parameter within Dremel. So let's go to a couple of conclusions before I run out of breath here. Number one is that you always want to be building software that is optimized for your use case. In their case, they realized that it taking a while for all of their analysts to run their queries is a big inefficiency, and they wanted to optimize for that. And so ultimately they did exactly that, and it worked out really nicely. They don't have to build some super generalizable distributed query paradigm. Even though Dremel can handle those queries too, it is mostly meant for these types, and that's the architecture reflects that. Cool. Number two is that Dremel is not meant as a replacement for MapRuce, but it is ultimately meant to complement MapRuce. As I proceed to go ahead and delete things. Insofar that MapRuce is still better for ETL jobs, but Dremel for these ad hoc queries is going to be very, very nice. And then finally, of course, like always, we've seen this in the MapRuce paper as well, we're going to have a major trade-off between accuracy and performance. So stragglers are always going to be an issue due to just bum hardware. And then finally, Dremel does actually implement a couple of approximation algorithms. So there are some problems that I've actually done systems design mock interviews for on my channel for the top K problem and like the count unique problem. So, count unique active users, count top K Spotify songs in the last month. Dremel does ultimately have the ability to do approximations for these because it's a lot easier to do than find the exact solution. Anyways, guys, I hope you enjoyed this video. Sorry we got into that big protocol buffers tangent, but for those of you who really are trying to figure out exactly how this works, I recommend reading the paper. It is dense, but it is dense in a good way, and I think it's an interesting one. So I'll see you guys in the next one, and enjoy your weekends.